For our second example of Lecture 14, we are going to look at a parallel resistor-inductor circuit. Notice that the parallel RL circuit is going to be identical to the series RL circuit modulo a change, because if we take a look at what we're sitting on, over here we have a Thevenin equivalent circuit, a Norton equivalent circuit, and over here we have a Thevenin equivalent circuit. So we realize that it really doesn't matter, Thevenin, which version of this we're looking at, we're going to have basically the same information. What we critically need to know is what one of these things is. We're going to solve for it, and then we're going to get the information that's important. So let's talk about our source current for a minute. Our source current is equal to 5 times the cosine of 30 degrees plus 5t. Again, this is degrees, and this is radians. So, if we want to understand our circuit, there's a few basic things that we can tell people right away that make our lives easier. First of all, this is a parallel circuit. All voltages in branches are equal. What does that mean? Therefore, the voltage across the source is equal to the voltage across the resistor is equal to the voltage across the inductor. And we use the same relationships that we had before. We know our impedance relationships, but we also know our differential equations relationships. And with respect to the inductor, the relationship that we're looking at is that the voltage in our inductor is equal to L dIL by dt. And that's going to be what creates the differential equation in this circuit. We don't have to recreate the differential equation each and every time, because in a first order circuit, they're always the same. It's always the same structure. So we can simply take a look at it and talk about the transient. We know already that the transient has a very simple format. The transient is C times e to the minus t over lambda. In an RL circuit, we've learned that lambda is equal to L over R. In this case, that's 5 over 25. And if we take a look at that, we're going to see that that's equal to 0.2 seconds. So our transient is therefore equal to C times e to the minus t over 0.2 seconds. The other thing we want to talk about in this circuit is a little bit of an understanding of what the AC signals are going to look like. How fast are they moving? So let's talk about the frequency in hertz. Why do we talk about the frequency in hertz? Because that leads us to the period in seconds. So we have 5 radians per second. We want to turn that into hertz, so therefore we're going to divide out by 2 pi radians, because we know that 1 hertz equals 2 pi radians. So this is equal to 5 over 2 pi hertz, which is equal to 5 over 6.28. And if you want an exact answer, that's 796 millihertz. So if it's 796 millihertz, then what is the period? The period is equal to 1 over the frequency, which is equal to 1 over 0.796, approximately equal to 1 over 0.8, which is equal to 1¼ seconds. Therefore, each period is 1.25 seconds long. And this is pretty much the information that's important for us to understand, because it gives us some identification of the system as a whole. And it's nice to see in this case that the period is significantly longer than the transient settling time, so we see that right away the circuit is going to settle very quickly, and we're not going to have any issues with problems with our signal. Once we've done this transient analysis, and once we've understood what we need to understand about the signals, the period, and what's important about it, we are ready to turn around and start looking at step 2, we're ready to solve for the steady state signal, in this case a sinusoidal steady state. So now we're ready to look at our steady state analysis for our circuit. Recall that in our circuit we have a current source. That current source has an amplitude of 5 and a phase shift of 30 degrees. And of course we know that the frequency is very important. This is operating at 5 radians per second. That has two parallel branches, one resistor, which has an impedance of 25 ohms, or a purely real impedance of 25, and one inductor. If we take a look at our inductor, we know that the impedance of an inductor is J times theta L, so that's J times a frequency of 5 times an inductance of 5, or just J25. So we're going to put that here, and unlike the capacitor, this is a positive number. Once we have this equation, we are ready to convert our circuit into a single impedance circuit. How do we do that? Very simple. We copy our source, and we realize that our two branches are in parallel. So we simply have to calculate 25 in parallel with J25. Looking at that, the equivalent impedance is equal to 25 times J25 divided by 25 plus J25. But of course, we see right away that we can pull a factor of 25 out of the top and the bottom, so we're going to be left with J25 over 1 plus J. We don't want to have a complex number on the top and a complex number on the bottom, so what we're going to do in order to fix this problem is we're going to multiply by the complex conjugate 1 minus J. We do that on the top and bottom, and on the bottom we're going to have 1 squared plus 1 squared, or 2, and on the top we are going to have J25 minus J squared times 25. Of course, J squared is just -1, so this is equal to 25 plus J25 divided by 2. That is the Cartesian form of what we're looking at. And of course, this time we're in ohms and henries originally, so we don't have to worry about any extra terms in terms of the K or the milli or the micro. They just fall out. So looking at this, the magnitude of our equivalent impedance is going to equal 25 over 2 times the square root of 1 squared plus 1 squared. So what I've done is I've taken the top, I've pulled out a factor of 25, left myself with 1 plus J on the top, 2 on the bottom, and simply taken a look at that. This is equal to 25 times the square root of 2 over the square root, over 2, which is just equal to 25 over the square root of 2. Of course, if we want our complex impedance, we also need to know the angle. The angle is fairly straightforward. The angle of ZEQ is simply equal to the tan inverse of the imaginary part over the real part. That's 1 over 1. And of course, the tan inverse of 1 over 1 brings to mind our favorite 45-degree 1, 1 root 2 triangle. So if we're looking at a 1, 1 root 2 triangle, this is simply going to equal 45 degrees. So we have two versions of ZEQ. We have our Cartesian coordinates, and then we have our polar coordinates. ZEQ is equal to 25 over the square root of 2 with an angle of 45 degrees. Mark those off and realize that that is all the information that we're going to need in order to actually turn around and solve our problem. So, what do we do with this equivalent impedance? We turn around and calculate the things that are important in the circuit. So we know the current in the circuit, and we know the total impedance in the circuit. So if we want to know what the voltage in all of the branches are, all we have to do is realize that this follows the phasor version of Ohm's law. So Vs is equal to Is times ZEQ. Now the reason that we converted ZEQ into polar format was because this is much easier to calculate that way. So we're starting off with 5 at an angle of 30, and we're multiplying that by 25 over root 2, at an angle of 45 degrees. That's fairly straightforward. We have 5 times 25 is 125 divided by the square root of 2 at an angle of, and remember that you multiply the magnitudes and you add the angles, so you have 30 plus 45, or 125 over root 2 at an angle of 75 degrees. That is the first of the 3 phasors that we need to calculate for the information that we don't already have. Now, once we have that voltage, calculating everything else in the circuit becomes really easy, because we know that the voltage of the source is equal to the voltage of the resistor is equal to the voltage of the inductor. So, if we want to get the rest of the currents in the circuit, all we have to do is pay attention to Ohm's law for current. So, let's look at the resistor first. The current in the resistor is equal to the voltage divided by the impedance of the resistor. That's fairly straightforward. 125 over the square root of 2, and we have an angle of 75 degrees, and we are going to be dividing by the impedance. It's purely real, it's just 25. Well, this is simply equal to 125 over root 2 times 25 with an angle of 75 degrees, but of course that's just equal to 5 over root 2 at an angle of 75 degrees. And now that we've shifted over a few things on the screen so that there's a little bit more space, we can calculate our final current phasor. The final current phasor relates to the inductor, and in the inductor we do the same thing as we did in the resistor, so that we have the voltage over the inductor impedance. That's just 125 over root 2 with an angle of 75. But this time we're dividing by 25, so the magnitude is the same, but we have J25 as our Cartesian value. The J-axis is just positive 90 degrees, so it's 25 with an angle of 90 degrees. So remember that we're dividing, which means that we're going to be subtracting the angles and we're going to be dividing the magnitudes. So this is equal to 125 over root 2 times 25 with an angle of 75 minus 90 degrees, which simply collapses down to 5 over root 2 with an angle of minus 15 degrees. And now we've collected all of the phasors, we have all of the critical information that we need, and we're ready to start looking at the time versions of each of these signals. Now, in the last page, there was a couple of computations that would have been rather hard to do without a calculator. But again, you can easily use graphs to figure those things out. So if you were to take a look at one of the things we needed to do, at one point we used the square root of 2. Now, again, when you're working with numbers, you can really leave that stuff in that format. But if you need to calculate it for some reason, or if you're asked to give an estimate by using these, then what you would do is you would take a look at 2 on here. It's roughly 1/5 of the way in. Draw it across and realize that that looks approximately like 1.5. We know that the square root of 2 is 1.4 something, but having said that, you get a fairly good approximation even by a tiny graph like this. Now, the other number that we had to use was the tan inverse of 1 over 1. So the tan inverse of 1, you would draw a line across 1. You would take that line, drop it down, and as you drop it down, you would see that the tan inverse of 1 is approximately equal to 45 degrees. So again, what you do is you take a look at the number that you're looking at, draw a line across it, find the point where that intersects, drop a line down, and that's equal to the number of degrees. So it's a fairly straightforward process. In fact, if you're going to do things with numbers, the square root, the tangent, and the cosine are all very convenient in order to do your calculations. You use the square root and the tangent in this part of the calculations, and later when you're looking at the time values, you're going to need the cosines. So, with that said, we're going to move on to solving the circuits for their actual time value. So recall you have the parallel RL circuit, and we know a lot about it. We've got the current, and that breaks up into two currents, one that goes through the resistor, one that goes through the inductor. We're told at the very outset of this that we have an inductor current, a source current, Is of t is equal to 5 times the cosine of 30 plus 5t. Notice that whenever you have one of these, first of all, you're assuming that it starts at time t equals 0. Second of all, you're not going to have any transients on the source voltage, on the source current, because that's what you're given in the first place. So the only time you ever have transients is on the things that you aren't given to start with. The other thing that you remember is we know a little bit about the structure of our circuit, so we know that the current cannot instantaneously change in the inductor. It can change in the other pieces, and we've got all of that. But at this point, we're simply going to focus first on writing down the full set of equations, and then once we've done that, we'll move onwards. We don't need the phasor for the source current because we've already got that as an actual time equation, and that's the goal of what we're doing in step 3. We do, on the other hand, need to realize that we're going to be looking for the voltage in all branches. That has a phasor of 125 over the square root of 2 with an angle of 75, and remember that's particular to the frequency of 5 radians per second. We calculated the the resistor current to be equal to 5 over root 2 with an angle of 75 degrees, and we calculated the inductor, that's an L, phasor, in order to know what that is. That was 5 over root 2 with an angle of minus 15 degrees, and we note that the inductor lags behind the rest of the circuit. It's 90 degrees slower. We also know that we have CE to the minus t over 0.2, so our time constant is 0.2, and that's the structure of the transient. So these are the steady states, and this is the transient. Once we have that, it's simply a matter of writing down each of the equations that we know. So we know Is, we don't need to write that down again, but we need to write V of t. We don't need to write which voltage it is because they're all the same in all the branches. This is equal to 125 over the square root of 2 times the cosine of 75 plus 5t plus some voltage constant times e to the minus t over 0.2. We know for our resistor that IR of t is equal to 5 over root 2 times the cosine of 75 plus 5t, again we've mixed degrees and radians, which is really sloppy, plus some constant times our resistor, e to the minus t over 0.2. Our inductor current is equal to 5 over root 2 times the cosine, this time the phase shift is different, minus 15 degrees, plus the same frequency, plus our inductor constant times e to the minus t over 0.2. So now we've completely defined everything in our circuit, and the one thing that I'll just remind you is that the voltage in the source is equal to the voltage in the resistor is equal to the voltage in the inductor. So in actual fact, we have 1, 2, 3, 4, 5, 6 equations for 3 elements. That makes sense. We need a voltage and a current for each of them. So we have the forms of the transients, we have the exact values for the steady state, and there is only one thing left to do in order to fully describe this circuit, and that is to figure out what those constants are. So, in order to find the constants, we're going to take a look at each of the equations and we're going to identify the initial conditions of the circuit. So to start with, we realize that because we have an inductor, the inductor cannot change its current immediately. So even if that current source turns on at 0, the inductor has a current of 0 amps at 0. Now, we also can simply plug in the value of t equals 0 into our source, which tells us that at our source, we have a value of 5 times the cosine of 30 degrees. So we take a look at 5 times the cosine of 30. This is equal to 5 times root 3 over 2. Plug that into our calculator, and this is equal to 4.33 amps. Now we need to look at the current in the resistor. And in order to understand the current in the resistor, we realize that we have basically a very simple KCL, where the current in the source is equal to the current in our resistor plus the current in our inductor. But of course the inductor current starts off at 0, which means that the resistor current is simply equal to the current in the source at time 0, so this is also equal to 4.33 amps. Now, with that current in the resistor, we're able to figure out the voltage in all the branches at time 0, because the voltage in the branches can be calculated by looking at the voltage in the resistor. V equals IR, so this is simply IR at 0 positive times the actual value of the resistance, which is 25. So looking at this together, we have 4.33 times 25, and that gives us a basic value of 108.25. So we now know all 4 of our initial conditions. We know the initial current, we know in the inductor, we know the initial current in the source, we know the initial current in the resistor, and we know the voltage in all branches. So we're now ready to turn around and solve for our 3 unknown constants. In order to do that, we simply at each stage evaluate the information at time 0 positive and plug in the left-hand side and the right-hand side. So we know that our voltage is equal to 108.25. We also know that that's equal to 125 over the square root of 2 times the cosine of 75 degrees plus C1, and we notice that when t is equal to 0, or CV, when t is equal to 0, that's just equal to 1. So we can rearrange this to solve for the constant. Therefore, CV is equal to 108 minus 125 over the square root of 2 times the cosine of 75 degrees, which is simply equal to, if you do the math, 85.37. Take that number, plug it into there. Do the same thing the next time around. Look at the resistor next. 4.33 is equal to 5 over root 2 times the cosine of 75 degrees plus CR. Therefore, CR is simply equal to 4.33 minus 5 over root 2 times the cosine of 75, which, if you do the arithmetic, works out to be 3.415. Take the number, plug it into there. Do the next one, and we see that the inductor current is 0. 0 is equal to 5 over root 2 times the cosine of negative 15 degrees plus CL. Therefore, CL is equal to negative 5 over root 2 times the cosine of negative 15 degrees. And when you do that arithmetic, because of the different phase shift and the different numbers, this is simply equal to minus 3.415. Take that number, plug it into here, and off and away we go. We've got everything that we were expecting to get. Now, a quick comment to note. We see that KCL works. We see that the voltages are the same everywhere. And now we have all the different pieces in order to get our equations. We have the actual form of the final function. So we're totally able to continue and actually calculate the voltage and current in any of the elements at any given time. The time that we're asked to calculate this for in this particular case is 10 seconds. Looking at our circuit, we're going to rewrite all of our equations one more time. The current from the source is equal to 5 times the cosine of 30 plus 5t. The voltage across all branches is equal to 125 over the square root of 2 times the cosine of 75 plus 5t, remembering that those are in 2 different units, plus 85.37 times e to the minus t over 0.2. The current in the resistor is equal to 5 over root 2 times the cosine of, again, the same phase shift, 75 degrees plus 5t. And this time we have 3.415 e to the minus t over 0.2. And lastly, we have our inductor, which is equal to 5 over root 2 times the cosine of, there's a phase shift here now, minus 15 degrees plus 5t minus 3.415 e to the minus t over 0.2. Now, we're going to take a look at the time, and we're going to see that the time we're asked to evaluate is 10 seconds. Notice that 10 is much greater than 0.2. In fact, that would actually lead to 50 time constants. If we have 50 time constants, we can very simply ignore the transients off the top, because at 50 time constants, those transients are going to be so small we don't need to calculate them. So the next thing we need to do is figure out what 5t is going to be, because we need to convert either the degrees into radians or the radians into degrees. Now, if t is equal to 10, then we have 5 times 10, which is equal to 50 radians. But if we're looking at 50 radians, then we're going to need to convert that into degrees. This is equal to 50 divided by 2 pi times 360, which is equal to 2,866 degrees. If we see that we have 2,866 degrees, we can subtract off 7 times 360, which is equal to subtracting off 2520, and that will leave us with 346 degrees. So once we've done that, we can now take a look at the problem and figure out what we need to do. So, taking a look at all of the different pieces, we see that the voltage at time 10 seconds is equal to 125 over the square root of 2 times the cosine of 75 plus 346. And that number up there is equal to 421. Subtract off 360 one more time, and you get left off with 61 degrees. So this is equal to 125 over the square root of 2 times the cosine of 61 degrees. That's approximately equal to the cosine of 60 degrees, which is approximately equal to a half. And, is approximately equal to a half. So when you take this, you multiply it out, what you are left with is 125 times cos of 61 divided by the square root of 2 is 52.1 volts. So now we're going to follow up with the same kind of calculation when we look at the current through R. So the current through the resistor at 10 seconds is equal to 5 over root 2 times the same cosine of 61 degrees. Now remember that the cosine of 61 degrees is approximately a half, so this is equal to 5 over root 2 times 2, and when you multiply all of that out together, you're going to get 1.7. Let's just finish multiplying that out. 5 divided by 2 divided by the square root of 2 is equal to 1.76. That's equal to 1.714. Now we're going to do the same thing, and that's in volts. Now we're going to do the same thing with our inductor. Our inductor current at times 10 is equal to 5 over root 2. And now we're going to take a look at the cosine that we have over here for our current, and it's a different phase. It's shifted 90 degrees earlier. Remember, 75 minus 90 was minus 15. So this is 61 minus 90, which is equal to 61 minus 90, which is equal to minus 29 degrees. If you take that and multiply it out, the cosine of 29 degrees is pretty close to root 3 over 2. So you multiply everything all together. You have 5 over root 2 times the cosine of 29 is equal to 3.09 volts. And now if you want to make sure that everything seems to line up, then we can do a quick computation to make sure that our KCL adds up. So KCL at 10 seconds tells you that 4.806 amps is equal to 3.09 plus 1.74, and in fact that adds up to pretty much exactly what we were expecting it to add up to. 714, sorry. We'll just drop it at the 1, and notice that there's some higher order terms, so this is going to be approximately equal because there's some rounding. This is equal to 4.804. That's close enough because we had all the right numbers everywhere. So we're glad to see that we have the numbers that we need. This is equal to V at 10. That's amps, not volts. This is equal to IR at 10. And apparently I wrote volts everywhere, so be careful with your units. And these are all the numbers that we needed to find in the first place. So now we have concluded our second example, and we see that just like the first order series circuit, the first order parallel circuit is reasonably straightforward to solve, and it follows the same types of patterns. After this, we've got one more example to go. We're going to be looking at second order series RLC circuit.